So yesterday we were seeing this e-commerce log analysis. Yesterday we saw how the producer code looks like, and we used to expose the API called publish API, and the client application can call that publish API, which will send each e-commerce log as a message to the Kafka cluster. That's what we saw. But when we tried to run that, we used to get some compilation errors. The reason that compilation errors we were getting is because recently I have made this log analysis to use Avro Serializer. The Kafka message that goes to, we know that by default it uses byte arrays, but we can send the data as string, we can send the data as JSON, we can send the data as whichever format. One of them is Avro format. So you serialize your data into Avro format or Avro class objects and then send the record to Kafka. So that is also possible. So usually what happens here is, just to give a background on that Avro serialization with respect to Kafka. Earlier we saw how Avro serialization works in Hadoop. I mean, Avro was created, origin of Avro was created in Hadoop. That's the base where Avro started. But Avro can also be used, Avro serialization can also be used in Kafka as well. Just like we have a a string serialization, we can also have a Avro serialization. Now, how does Avro serialization work? If you remember, in Hadoop, you used to send the schema along with the file, along with the data. So you will have the data, Avro data, in the form of key value pair. This will be your Avro data. Along with the Avro data, if you remember, we used to also send the schema. The whole, this is how the data is stored in Hadoop ecosystem. But can we do the same thing with Kafka also? Because in Kafka we are not storing a whole data. This data could be a 1 GB file, or it could be 10 GB file. For 10 GB file, specifying a schema which is in bytes, that should be good enough. There is no problem in that such. The schema size may be in bytes. So it will just add few bytes to the 10 GB of data. So that is fine. But in case of Kafka, what happens? In case of Kafka, what happens? You have a producer, you have your Kafka cluster, then you have your consumer. So producer has to send the data, and before sending the data, it has to do Avro serialization. Now consumer has to consume the data, it has to do Avro deserialization. It has to do Avro deserialization. Now the Avro message is only in, usually it will be in KBs. Avro message will be, sorry, each message that you send from a producer to the Kafka will be in KBs. Usually message size will be KBs. Along with that, if you start sending the Avro schema also, it may double the size of your data. So it is not a good idea to send the schema along with the data itself, Avro schema. So how do they handle in that case? So in that case, the Confluent company has come up with this. All this Avro was included because of the Confluent company. There is something called as a schema registry. Schema registry is a web server running on some 8001 port. Schema registry is that. So what they do is there will be .avc file, some log which will define the schema. There will be some avc file which will define the schema here. Sorry. Where we will have a schema defined in the form of a JSON. Using that schema, we know that how to generate the code. Code has to be generated. Last time when understanding Hadoop, we saw code generation. We did manual code generation for a given schema. Now using that code, you copy the data. You convert your message into a Avro record. Avro record and the schema during that Avro serialization. We have this log.cs avsc. We have this log.avsc in our producer code. So using that log.avsc, code is generated. After code is generated, producer will send the message and use the code generated, convert it into Avro message. We have the normal message. We use the Avro AVSC file and the code gets generated and it is converted into Avro message. Then the Avro serialization. The serialization comes into picture. In that serialization, the Avro message is serialized. During the serialization, it connects to the schema registry. What it does is it stores the schema here. It stores the schema here, and from here it gets a unique ID for that schema. Sends the schema here. Will be stored in the schema registry, and from there it will get a response, a unique ID for that schema, and that unique ID is sent along with the message. Here. So the unique ID is in it could be a long integer. That's all, which will not increase the message size by very long. I mean, it will not make the message size double or something. Slight one unique ID will be included.
Oh, Pramod, what is that? A log.avsc? It is a schema, Avro schema.
Right. It is a Avro schema. If you remember, we saw while seeing the Hadoop. It will be something like this.
It applies for all the messages, right? This schema. Okay.
So this is the Avro schema. If you remember, we also saw these things in our Hadoop while defining the format. We saw first text format, then sequence format, then Avro format. So Avro will have this AVSC file.
So we have to give this format Avro first.
Correct. The we have to specify this format.
Okay, then how the code is generated?
Code is generated. If you remember, we generated the code using the jar file. If I go to download Avro, so if you remember, I'll just remove this from. You use the Avro jar. If you go to the jars folder, so there is something called as a some jar file. So this code, this jar file will generate the code actually using the schema. I have some schema here. Let me show that schema. This is not the same schema. Some sales schema, sales.avsc we have. We have a sales.avsc. Using this schema, we can generate the code. So here is the command to generate the code. We have to run that Java code, Java hyphen jar, specify that tool jar. What we want to do, compile the schema, and where is the schema? Schema is inside the schema folder, and the schema file name is sales.avsc. And you want to specify where you want to generate the code, the output. I want to generate the code in this folder. So if I run this, enable, okay, I'm in the schema folder. So if I go to code gen now, so we can see that com data spark test avro sales.java. This code got generated.
Oh, it generates the Java code.
Correct. It generates the Java code through which you can convert a normal record to a Avro record. Normal record to a Avro record. So because it has all these fields there.
So this code is the Avro serializer code.
No, this is not the serializer. This is converting a normal string message to a Avro class object. You will convert into this class object.
Okay.
So that's what we do here. So that's so you take the log.avsc, code is generated, you take the message and convert into a Avro class object message. Then you send it to that Avro record is serialized now as bytes, because serialization is all about converting into bytes because Kafka understands bytes. So this Avro message or Avro record is converted into bytes here. That is byte arrays. So that's what the serialization is about. So during that while it is serializes, you don't have to include the schema here because your message itself is very small now. Along with that, if you start including the schema also, your message may double in size. So we don't want that to happen. So what they have come up with is they store the schema in the schema registry, and the schema registry will return a unique ID for that schema. It may be a long integer. So you just include one long integer along with your message, probably some 8 bytes. That should be fine. And then send it to the Kafka. Then send it to the Kafka. So the one that I have showed here is we manually we manually created this avro.sales. Yesterday we got the compilation errors because this code was not generated. Yesterday the code was not generated. That's the reason we were getting those errors. So we have this Apache log events.avsc, which has all these fields, and that code is not yet generated, and we don't usually manually generate the code. We put it inside the form.xml so that automatically the code gets generated. So there is something called as a plugin. Using this plugin, Avro Maven plugin, specify the schema where the schema exists. My schema exists in this path: project base directory, source, main, resources, Avro, which is nothing but project, source, main, resources, Avro. Inside that I have this schema file, and it outputs the code generated. So the where the code generation happens here is, it happens once you compile or create a jar file, the code generation will happen. So as of now, you can see that as of now, if I see Spark streaming, this is the normal Spark streaming. This is Avro with Avro file, but it will give some errors. Eleven or one second. Let's see what we are using. Scala version. Scala version is this. Okay, that should be fine. Here is a question: what is the use of Avro Java class? So it will convert your normal message, which is in the form of a string, to this class object. Instead of sending a string as a message, you will be sending a class object as a message. Your message is a class object now. So we can see that. I hope that was the question. Correct. Every line in a file, we are not sending a file now. You can assume that each message, instead of saying every line, because we are not sending the content of a file now, we are generating the messages. Those messages is converted into this Avro object. You can imagine, if at all we were sending a file, then it will be each line. But in this case, we are not sending a file. We are generating a messages. Each message will be converted into this class object. Later, it will be serialized. So as you can see here now, there are a lot of errors because that code is not yet generated. So this class is not yet generated, and I'm using that class. I'm using that class to get the records. From log generator also, you can see that we have a Apache log generator Avro. This was done recently. So while sending the data, so earlier we had only publish. Recently I've added publish Avro record. So we were sending the data as it is. Now we are sending the data as a Apache log event. So you can see that publish Avro record. So as of now, take all the Apache logs. So this code is not yet generated. You can see here this code is not yet generated. That's the reason we were getting the error. So we cannot do a manual code generation. Usually I showed the manual code generation of how Avro works, but usually all those things should happen automatically. So that's the reason all those things are included in the form.xml. Right, Apache log events will itself have the schema. That itself will have the schema. So using that itself, the code is generated. We will include that schema into the. I mean, we don't have to include that schema along with the message. That's the reason we are using a schema registry. Apache log event, the class that gets generated, the Java class, it will have a definition of the schema there. That's true. So what we'll do here now is we will run this program. I mean, we will uh, create a jar file, because when we create a we have to go to the view tool windows. From the tool windows, Maven project, and you will get this log analysis. Select on the package, run this. So it will create a package. So creating a package means it has to compile the code. So before compiling the code, it will use that Maven plugin, form.xml, the plugin that has been added for Avro. First it will generate the code and then it will compile. So we'll see where the code gets generated. So if you go to the target, this folder gets created as soon as you uh, uh, as soon as the build is complete. Now if you can see here, all the error has gone. All the error has gone because this code got generated. So where is that code? You can see here, generated source. In generated source we have Avro, log analysis Avro, Apache down, log events. So this is our Java file. This is our Java file. That Java file defines the schema also. Using this schema we can get the schema. This defines the schema as well. So if you go to the log generator, in the log generator you can see I also have the Avro log generator, which will I have the publish Avro record. So using that generated records, I'm saying apache.event.set IP set client. So we are having a record. We get our Apache log event. So this Apache log event is our actual record. It's a class object, which the message is converted into this class object, and we have to send to our Kafka. So we are creating a producer record because Kafka understands producer record. So where the value will be key is our string, normal, nothing is there actually. Value is nothing but our Apache log events, which is this class object. So we use the Avro producer and send the data. I'm hard coding the Apache log events. We can read it from our file also. So I hope this the reason that compilation error we used to get is because of this. I haven't completed the whole thing. So when the consumer wants to consume the data, so it is Avro serialized, means that the Avro messages are converted into byte arrays. First we need to convert that byte arrays to Avro message as a Avro class object. So we have to deserialize that binary to a Avro serial. So inside that deserializer, inside this deserializer, it will connect to the schema registry, specify that for this ID, give me the schema. Because that ID is sent along with the message here. This unique ID is sent along with the message. That message is available here. The Avro deserializer will connect to the schema registry and it will specify the ID. All these things happen internally. We just have to specify Avro serializer, that's all. So if you see here in the code, so we have created a Avro producer code. This is the same producer code, but the producer is not a normal producer now. Earlier we saw string producer, now it is a Avro producer. Bootstrap server remains the same, but if you see the serializer is, for value we are specifying the serializer as Kafka Avro Serializer, and it is developed by the Confluent company. So this we have to specify as a Avro serializer, and in case of consumer we have to specify Avro deserializer. And we need to specify one more important thing is where your schema registry is up and running. It is running on the port 8081. As I said, it is a web server. It will be running on HTTP 8081. That's the default port of a schema registry where the serializer will connect to the schema registry, specify the ID, store the schema, and get the schema registry will send a unique ID for that. That unique ID is again the deserializer will connect to the schema registry, specify that ID, and get the schema. From that, it will get all the messages. Finally, we'll get a Avro message, which is a class object. We can do anything. The consumer can do anything with this. Consumer can do anything. This is how Avro works in Kafka. It's a slightly different way that works in Hadoop. Here it's a way different it works in Kafka. But I hope you got understanding of how things works in how Avro is being used in the Kafka here. The mainly reason is the schema registry, and this schema registry is part of Confluent here. If you download the Confluent Kafka, so you will get the schema registry along with that. But if you download the normal Apache Kafka schema registry is not part of that. You have to explicitly download the schema registry from the GitHub, compile that, build that, integrate with your Kafka, then only you can use Avro with your Apache Kafka. If you are using Confluent, it will come built in, so you don't have to worry of building anything. So I hope that was clear. So we will not see it works fine. It works fine. We will not use the Avro one. We'll use the normal thing or whichever is fine, because in this image, I don't have Avro, I think, or Confluent Kafka. OPT, do I have Confluent here? Kafka 010, I have 08, I have. Confluent is not there. In this virtual box, I don't have Confluent. You can just download that also and can try it. In my other machine, other VM, I have that Confluent. But it's around some 300 MB, I think, 300 to 500 MB. You can download that and you can test that. That works fine. So we were about to see how the code generation works here. So let's see how the code generation works. We'll normally generate the normal code. Apache log generation Kafka. So here we don't have publish Avro. We will just not do a normal publish. We are just sending the string as it is. We don't require publish Avro. So I will run this. So before running, we have to have everything up and running. I'll just start the Zookeeper server. So let me check which path is being configured here. At 0.9 itself. Config zookeeper.properties. This will start the Zookeeper. Kafka server start config server.properties. Start the Kafka server. We'll also create a topic here. Topic will be something else. The topic will be nothing but the topic is given inside the resource file. If you go to the loganalysis.properties, we have the topic name. So we'll send the data. We'll keep the partition 1. I mean, whichever is fine. 2 or 1 doesn't matter. So the topic is created. We can check that as well. If I go to the temp folder, Kafka log, so Apache log events 0 is there. So we have 0 bytes here. We have 0 bytes. If I do a tail on that, so we should, as of now, nothing is there. As when I said that the messages we send, it will get appended to this file in the Kafka broker. So this tailf will just display on the console the contents of that file. Whatever gets appended, it gets displayed here. Just for our verification purpose, we can check that. So before creating, let's see what is the input parameters we have to pass. If I go to the main method, it takes number of records that I want to send. Kafka broker list may not be required, I think. Okay, I could have read this from my code, from the configuration parameter and the topic name. So these are the three parameters we need to send. Number of records we want to send. Number of records, let's say how many per day. It is number of records per day. So how many records, if I want one record per second, per minute there will be 60 record, per hour there will be 3600, per day, so 86,400. We will be sending 86,400 records per day, which will come to almost 1 second, one record per second. Our broker is, I mean the Bootstrap server. We are specifying the Bootstrap server, and our topic is Apache log events. So these things, I mean, I did not make the code changes, but all these things you can read from the configuration file. We don't have to explicitly specify here, but I did not make that changes, but you can always. So as you can see, per second a record is getting generated. So this is our Apache log. This is the simulation program I was trying to say here. So you are getting this Apache log. You can also see that this is getting going to our the Kafka cluster. From the producer, it is going to the Kafka cluster. Whatever is generated here, we are pushing it to the Kafka or publishing it to the Kafka. So this is how a message queue kind of a thing works. Continuously, we are sending the message. Every 1 second, a message is being sent to Kafka. We can increase the number of records. How much records you want to send per day, you can increase it, in which case more records will be sent per second. Now the Spark has to consume this data. On the other side, we have our Spark consumer. We have our Spark consumer. So we can check the log analyzer Kafka stream. So we saw these things. We saw the simulation program, and we saw the producer code, how the producer code looks like. We will see the consumer code now, where the consumer is embedded inside the Spark streaming application. We know how to how the Spark streaming works, we need to specify the batch interval. We need to specify the batch interval, create a streaming context, and get all the, I mean, then using that streaming context, connect to the Kafka cluster and start consuming the message from that. So as you can see here, we are using this properties file. We are using this properties file, and no, once the message is consumed, it is not deleted from the Kafka. It will still be there in the Kafka. The main idea is to represent it as a central repository so that some other consumer, some other application can also consume the data from that same data. Multiple applications can consume, so it will not be deleted. So as you can see here, we are reading everything from our properties file. Will there be any housekeeping in Kafka? Housekeeping in the sense, I didn't get the question, Mohan. Cleaning of old messages. Yes, yes, there is a time limit on how much time a message can be there on the disk. So it is usually 1 week. After 1 week, that message will be removed from the disk. Retention time, correct. After 1 week, it will be removed automatically. Yes. So you can configure how much time you want to have your data persisted. So you can specify that as 2 weeks or 1 month based on your requirement. So all those things are there in the configuration file of Kafka. If I go to server.properties, you will see in the server.properties log retention hours. It is 168 hours, which will come to 1 week. So you can specify how much hours you want to retain your data. After this is done, it gets deleted. So the way it gets deleted is, there is a trick there again. So if you see log segment bytes, it is 1 GB. What does this mean? There is something called as log segment bytes, and it is 1 GB. What it means here is, this file can contain maximum of 1 GB. The records that we are appending to this file can contain 1 GB of data. As soon as 1 GB is over, it will roll over. It will roll over and a new file will be created. And when it rolls over, this it will be renamed with the latest offset, start offset and the end offset. So this log contains offset also. So it will be renamed as soon as it rolls over. It will be renamed with the name as, from the start offset to the end offset. So we'll get to know from which offset to which offset this log file contains. Then again a next file, one more file gets created. Now that log retention is all about, this retention we are seeing as 168 hours. after the rollover happens, and if that file is 1 week old, then that file will be deleted. So I hope you got the understanding here. Just to put it on the, so usually it will be file will be 00 some dot log here. So this file will be open. This file will be always open because the producer has to write the data, and some consumer has to consume the data. So this file will be open here. So somebody will be writing the data, somebody will be reading the data. Multiple reads, multiple consumers may be reading the data. Till what time they can read? So after 1 GB is full, because we have specified the log segment size has to be 1 GB. As soon as 1 GB is full, it will have the offset. It will be renamed to, let's say, the offset was some 2000, something like this. So it will be renamed in this fashion. Now again, the next file will be opened. One more file will be opened, to which the producer will start writing the data. Now this file must be so only when after 1 week this file will be deleted. So I hope, Mohan, that was clear. This is how the deletion happens. It is the segment that file is deleted. If that file becomes 1 week old, then it gets deleted. But again, it may not get deleted after 1 week immediately, because it may happen that this file may not be 1 GB at all. Probably you are not getting lot of messages to your Kafka for this topic. You are getting very less messages. Let's say it took 1 month. It took 1 month for 1 GB of data. So your input rate was very slow. The application which are sending data to Kafka, they are slowly sending the data. So till it is closed, it is not deleted. Till it is closed, it is not deleted. So even after 1 month, this file still exists. That 1 week, 168 hours that is given only after it gets closed. So only after this gets closed, I mean, after 1 month it gets closed, because it was full with 1 GB of data. From here, again, 1 week it will wait. Then delete. So you can see that the file got deleted after 1 month and a week. So this is how that housekeeping or deletion happens from the Kafka. Correct. 1 week after the segment file is correct. That's true. Segment file is closed. So we call it as a segment file. So those things are called as segment file. A partition is nothing but a group of multiple segment files. You can test it by setting the bytes. You can set the bytes to 1 MB or 2 MB. You could immediately see that multiple files starts getting created. So per partition there will be multiple segment files. So let's see the consumer code, what we have as a consumer code. So since we want to consume the data and save the processed data into Cassandra, we also want the Cassandra key space. Key space is nothing but in Cassandra word, for a database we call key space. In MySQL we say database, here we say key space. There is some lookup file we want. Lookup file is nothing but we want to convert a IP address to some country code. So if you remember, using this using this file, we are generating our IP address. You will see that the first two octets will be from this file. Whatever IP address I am simulating, I am generating, it will come from the first two octets will belong to randomly chosen some IP address here. The next two octets, these two octets is randomly generated, but these first two octets is taken from this file. First two octets. So in the consumer, what we want to do is, in the consumer, we want to take this file, get the IP address and its corresponding country name, so that we can get to know from which country we are getting more and more requests. So that we are reading here. This is our lookup file. So we are also reading our topic. All these are in our configurations file. So we got our topic. So we have our master, which master we are creating a Spark configuration, setting the master, setting some application name. You can also specify your application name in your configuration parameter. Cassandra, what is the Cassandra IP address? The way we give a bootstrap IP address so that any application knows where a Kafka is running, in a similar fashion, you give the Cassandra. Here we just say connection.host, Cassandra connection host, which is nothing but similar to our bootstrap. You need to specify the IP address and the port of Cassandra where it is running. At least we specify two, because at one time if one node is down, we can always connect to another node of the Cassandra cluster, because Cassandra is also a cluster. So max rate per partition is all about, at max, how much data you want to get per partition. So we can set that at max I want 1000 records from Kafka to Spark per partition. I mean, it will not go beyond 1000 records. We are having Kafka. We have uh, Apache-0. Let's say we have three partitions, Apache-1, and we have Apache-2. So we have a Spark. So we have an executor here. Inside that executor, we have a task. Here also we have an executor. Here we have a task 2. Here we have an executor. We have a task 3. This is broker 1 handles this. Broker 2 handles this. Broker 3 handles this. This is our Kafka cluster. This is our Spark cluster. So it will be connecting, the thread will be connecting to the broker here. And they will be sending the request that from this topic, from this partition, send me the data from a particular offset. And here we have max rate per partition. If the max rate per partition is 100, let's say max rate per partition is 100. So we are, our batch interval is, let's say 1 second. Our batch interval is 1 second. So means every 1 second it will be whatever data it receives in 1 second, that will be processed in the next 1 second. It will be getting the data for 1 second. As soon as 1 second is over, one batch will be created. So in 1 second, it is saying that at max, I want only, let's say 1000, not 100. At max, I want 1000. Max 1000 records. Even if more than 1000 records are available in Kafka, if the producer is much faster, if the producer is sending data, is sending at 2000 events per second. Producer is sending the data at 2000 events per second per partition. So we will have more than 1000 events in our Kafka cluster. More than 1000. But in every batch interval, we will be only receiving 1000 events. Let's say our consumer is a bit slow. We don't have enough resources in our Kafka cluster. So it will be only receiving 1000 events per second per partitions. So totally we'll be receiving 3000 records. So that's what that max rate per partitions specifies. Even if you have the data more than that, you will be max rate per partition. No, max rate per partition is for consumer. It is not for the producer. It is for consumer. At what rate you want to consume the data? We want to consume the data as at 1000 events per second per partition. So in total it will be consuming, since there are 3 partitions, it will be consuming 3000 events per second at max. I mean, it may not have 3000. Let's say if your producer is very slow, if your producer is sending at a very slow rate, probably it will have only 100 records. So in 1 second, it may get only 100 records. It will just return with that 100 records. So partition 2 also will have 100 records. Partition 3 will also, let's say, 100 records. So it will have 300 records. So it cannot cross this boundary. Below this, any number of it can have. So that's the idea of max rate per partition. So other things are Cassandra related things. We can see these things later. So this is where we want to save our data to this Cassandra database. We will see this later. So using that configuration object, we are creating a Spark context. This is not necessary, but explicitly also we can create a Spark context. Using that Spark context, we are creating our streaming context. So we had already seen how to create a streaming context. Using Spark context, we are creating a streaming context. Now here, if you remember, we learnt about broadcast. So broadcast is all about sending the data from the driver to every executor. So why we are using a broadcast? Batch interval is in seconds. We can specify seconds, minutes, milliseconds, any interval you can specify. But in this case, we have specified batch interval as milliseconds also we can specify. Let me check whether there is a There is one more project embedded inside this. This is a different one. This is not a log analysis. So you can read the configuration file. If you specify in seconds, you can say seconds duration. You can specify milliseconds duration. You can specify minutes duration also. Let me check whether that configuration file is available. So this is a different project where we are reading the data from Kafka and saving it to HDFS, where a Hive table is created. Later they are giving the query using the Hive table. So you can specify what is the type of, whether you want seconds type, milliseconds type, or minutes type. When it is seconds, it means 3 seconds. If it is a minutes you specify, it will be 3. These things we are reading. This is our configuration file. We are reading that configuration file, getting that duration type. If it is a seconds, we are creating a duration in terms of seconds. So I hope through that was clear. You can specify in any form. It's all in your hand. So now we were seeing about the broadcast. So why broadcast is required and what we are broadcasting? We are creating a hash map. So if you remember in our join operation in Spark RDD, in Spark core we talked about join, and in that we had our broadcast join. So what we used to do there, so if you remember, so if you see now, this is our executor, this is our executor, this is our executor. This is our Spark cluster. Again, we have our Kafka producer here. Sorry, broker 1, broker 2, broker 3. So we have our Apache -0. Let's say we are having 3 partition, Apache -1, Apache -2. So what does this contain? Apache log, whatever code we are generating, whatever data we are generating, it has the IP address here. So our task is consuming those data. Task 1, task 2, task 3 is consuming the data from these topics. So what it is consume? Each record. Now what is each record? Each record is nothing but, this is one record. The whole thing is one record. It has the IP address. The analytics that we want to do is, we want to know from which country how many views we are getting. Those are the analytics. IP address, we have a IP address to country code mapping file we have. Using that file, you can get to know from which country we are getting more and more requests. But that, since that is a file, that is a file. What we are doing here is we have a driver. Let's say we have a driver. We have executors and we have the drivers. The driver creates the DAG. All those stuff remains as it is. Now inside from the driver, we are reading that all class file. We are reading this all underscore class ps dot txt. We are converting this to a hash map. We are converting this to a hash map. We are reading this file, convert into a hash map where key will be the IP address, value will be the country name. 1.3 maybe some China, something like this. So we are creating a hash map, reading this file and creating the hash map because we want that to be available on every executor. Because in every executor we are receiving our log messages. Then we make it as a broadcast object, and that broadcast object will be sent to every executor. So hence we have this IP address to country code mapping available in every executor. So then we will go through this code. We'll open that broadcast object. We'll look for that IP address and we'll get a country name. We'll get the country name so that we can get to know from which country we are getting this request. So that's the reason we are using a broadcast object here. So we are creating a map collection. We have we have defined an utilities object class. As simple as we had earlier done that. We are creating a hash map, reading the content of the file, going through each line. We split it by space. Because it is space separated. When we split it by space, it returns an array. First element of the array is the IP address. Second element of the array is the country code. We split it by array. It returns an array. First element of the array is the IP octets, the first two octets. Second element of the array is country code. So that we need to put inside a map collection. We are putting that as the key is this IP octets, value is, and we return the collection map. As we used to do it for our join operation, here we are doing the same. And then create a broadcast object of that map collection. We got our broadcast object. So this we are keeping and do. We have created our broadcast object now. We haven't started our streaming application yet. Now we have to connect to Kafka. So we need to specify some Kafka configurations parameter. The consumer has to connect to Kafka. So we have the Bootstrap server. Again, we are reading from the file Bootstrap server. As I said, every application will have a application ID. Sorry, group ID. If you remember yesterday, we talked about group ID. Group ID is all about an application. One application will have a unique group ID, so that multiple applications can consume the data from the same topic. Same topic they should be able to consume. So there should not be any ambiguity in which offset is being consumed from a consumer from one application and a consumer from another application. So based on the group ID, they will also figure out from which offset the consumption should happen. So group ID is some unique name we have given. You can check again here. Somewhere we need to have the group ID. Application name is this, group ID is some login data processor, some name. That's all. That's how we specify a group ID. Serializer is, as usual, string serializer because we are sending the string. If at all it was a Avro, we were sending a Avro record, then this would have been changed. The value would have been changed to Avro deserializer. So we can check that as well. So if that code is also here, you can check. We have log analyzer Avro Kafka streaming. So in that case, if you see the value serializer, it is Kafka Avro deserializer. Otherwise, we use a string. Because we are sending the string, we need to have a string deserializer. Since in Avro we also need to specify the schema registry, we say that schema registry is running at 80814. So these are the configuration parameters for our consumer. So we have to specify the consumer. Now we are manually storing the offset to the zookeeper. That's what I said. We are manually handling the zookeeper here. I mean offset management. You can save it anywhere also. I'm just trying to show how to save a offset to an external storage manually. So for the case of zookeeper, we have to create a offset store. We are saying zookeeper offset store. If you see that code is available here, log generator offset source, where you want to save the offset. In offset we have stores. Offset store is some trait. We have defining a trait here, so which has read offset and save offset. Some offset store. So if you want to have a zookeeper offset store, you extend it from this offset store. So we are having a zookeeper offset store which extends from the offset store, and it has to implement now that save offset and and read offset. So as you can see here, the read offset, read data, maybe null, we are trying to read the data from our zookeeper. These zookeeper utils are there, so we have to have these utils. These are all the zookeeper's APIs. You need to understand how the zookeeper APIs work. So we are reading from that path, or before reading that from path, first we need to create the offset store. We are creating a zookeeper offset store, and the location we are specifying as Kafka. / Kafka, meaning here the Kafka gets created. If you go to zookeeper shell, so as of now there is no Kafka here. As of now there is no folder called Kafka. So anything you want to store in a zookeeper, first you need to create some folder there. Only inside that you can store anything. So that's what we are trying to do here. Zookeeper store, the path is Kafka. The path is Kafka. Once we create, so that just creates the object of this class. Object of this class. What is the zookeeper path? Where the zookeeper is running, the IP address and the port. We need to specify. Just create a zookeeper client here. some timeouts are specified here. What it will do is it will read from this path whether a offset exists or not. I mean, the very first time when you start this application, consumer application, there may not be any offset at all, because the very first time there will be no offset. That's where you start writing the offset. So there could be none offset or some offset. So we are passing the return value. This is the return value from that read maybe null. From this returns a tuple with the first value containing the offset. So there could be some offset. We are using the option monadic collection. If you remember, we learned about Scala option monadic collection that is being used here. So we are reading the offset. If the offset exists, get the offset from there. Partition, offset, we have all these things. I mean, the way it is stored is we will see that. We will see that how it is being stored, so that we have to write this code to get the offset and just. Finally, we'll get the partition number and the offset number. And we will return that offset. We'll return that offset. If it's not there, we'll just return none. We did not get anything from the offset. We did not get any offset from the zookeeper. In that case, we'll say no offsets found in the zookeeper. Hence, we return a none in that case. If it is a none, we will return a none. This is how you read offsets from the zookeeper. This is how you save your offset from your zookeeper. Reading happens only during start and restart. Reading happens only during start and restart, but write happens every time you consume the data. So every time the Spark application consumes the data, that data will be in the form of an RDD. The data will be form of an RDD. Hence, from that RDD, you have to have it in the form of a as offset range. Convert means convert into an instance of as offset range, and from that get the offset range. Get the offset range, and these are all the prints we want to specify. Using the zookeeper utils, update persistent at offset string. This is how we are saving the offset. Offset partition colon offset number. Offset partition and offset number. That's how we are saving the data into this path. So these two are should be used in our Spark streaming. This is an independent module. Read offset and write offset. Read offset and save offset. These two codes should be called from our Spark streaming application. So these two things has to be called from our Spark stream. So we are using this Kafka source where these two things are being called. So read offset, and you can see here save offset. So how it is being used here? How it is being used? So this read offset, we already saw this code now. Either it returns the offset or it returns none. Either it returns an offset or returns a none. So this is the code to connect to your Kafka cluster. Create a direct stream is the code used to create a connection between your Spark streaming and the Kafka. Internally, everything will be handled. This one API is enough. This one API is enough to connect from the Spark streaming to your Kafka cluster. Now how do we handle such that there is sometimes offset is there when we start the application, which connection has to be established, and during the normal processing where it has to happen. I mean, when we start the application and when we restart the application. Since the very first time there will be no offset in the zookeeper. This read will return none. This read offset will return none for that topic. So we'll go to that none case and we just establish the connection to the Kafka, where it will start reading from the zeroth offset. Since there was nothing there, it will start reading from the zeroth offset. No offset was there. And it will continue reading from that offset. The normal things will happen. Every new request will go from zeroth offset to probably fifth offset. Then it may go to 20th offset. It will normal go. Now, when you restart your application crashed, and you restarted your application. Again, this read offset method will be called. This time, it will return some offset. So this time it will not go to none. It will go to this case, some offset. So it will use this offset while reading the data. Create a direct stream, specify the streaming context, specify all the configuration parameters, then also specify the from offset as well. So this is our streaming code. As soon as we read the message, save the offset. So if you see here, after reading we are saving the offset, or we are just reading the record and we are saving. Offset is saved. We have already seen the save offset method, which takes the RDD. From that RDD will get the data. We will see. I think we haven't discussed about for each RDD. We will see that. Offset is saved as soon as data is read from Kafka. So the better way to say this is saved before processing and saving data. So you can see that we have just received the message, because this will return a D stream, create direct stream. Just like we had text stream, socket text stream, here we are using the create direct stream. You will get the stream here. This Kafka, this is nothing but a D stream of your input data, key value pair, where value is our actual record. The value is our actual record. So here we are saving, the offset is saved before processing and saving data. So what does that mean? It means there could be data loss. It is at most one semantics. So there could be data loss. So if you save this offset after you have done all processing and after saving the data to Cassandra, if you call this method, in that case, it will be at least once semantics. So I think that code should also be there in our Kafka streaming. I mean, I have commented that. I think I have written it in my Avro Serialization. Lot of code changes. So this is all saving into Cassandra. The process data is being saved to Cassandra. So if the saving of Cassandra is done here, after saving the data, saving the offset after processing and saving the data. So this is at least once semantic. So there could be duplicate data on restarting the application. If you put it at the end of this, at the end, so you will be having duplicate. If you put it starting itself, you will have a data loss. You will have a data loss. So as you can see here, we have created an offset store. This Kafka source, Kafka stream is nothing but where we have defined what happens during the restart and when the normal start. So this is during the start. This is during the start. This is start from the previously saved offset. All that code is available in the Kafka source. That code is available in the Kafka source, which is nothing but this file. So this method, we have defined this method Kafka stream. So this method will be called in your application. If you see here, first we set up the zookeeper offset. There we have written the read and write, and later we are class tag is nothing but we need to specify the serializer and deserializer. We need to specify the deserializer. Even I know we have to specify the what type of serializer and deserializer we need to specify. So to specify that internally, we need to specify the class tag. I mean, not much clear on that. I will to explain. I am not much clear on that. Let me get more clarity on that class tag, then I will explain. Probably if Ashok has a good understanding on that, probably he can. I will try to explain that. I mean, I don't have a clear understanding on the class tag. Once I have, I will surely explain. So what we have here is it has hanged, I think. No. So this is our Kafka stream, this method that I was saying. So this specifies the class tag. This specifies that your key is a string. Your value is a string. Your decoder is a string decoder. Your key decoder is a string decoder and a string. Your value decoder is also a string decoder. So that we need to specify. And we want only the value part, hence we are saying dot underscore two. We don't want the key part because there is nothing in the key. Our actual data is in the value. So we are getting our value part. So internally everything will take care of reading the data from Kafka offset and saving the data to offset. Everything is there defined in this function. When we start and restart, everything is taken care of. It will just return you this method This method will just return you the actual message, log stream of a string. So some messages could be error messages, some messages could be good messages. We may have a error message, you may have a good message. So you have to parse, it is a string, right? We have to parse it. It is a string, we have to parse each message. So the way we are parsing is we are using a regular expression to parse our record. If you are using Avro, these all parsing is not required at all, because in Avro it represents a class object. We just get the class. It will be much easier when we are coding the consumer in the Avro file format. It will be much easier. Everything is internally taken care. Otherwise, your string may contain some error messages, or your string may be good or a bad record. So you have to parse your Apache string. And I mean, this message that we are getting, some messages may be good message, some message may be not a, a good message. So you have to parse that. So to parse an Apache log, there is a standard format, a standard regular expression exists to parse your Apache log. This is standard. You will get on the internet the standard way to parse a Apache log. So this is the regular expression used to parse that. So this represents IP address. This represents the user ID. This represents the client ID. This represents the timestamp. This represents get method, get or post. This represents the request URL. This represents the HTTP version, or we can see here itself. So we can see that user time IP address, then a dash is there. Dash is nothing but user ID. Then we have some client ID and timestamp. Then we have a get method. Then we have the request URL. Then we have HTTP version will also come there. Next we have the HTTP version. You can see that. After HTTP version, this represents the response code, whether we are getting 200 OK, 404 not found, all those stuff. This represents the content size. Content size. That's the standard pattern. This is the common pattern to parse an Apache log. Here referrer URL and user agent is not included, but we can include also that, but we can specify one more pattern as a combined pattern, which also includes last two again. This includes the referrer URL. This will parse your user agent. So we have to just parse our record with the help of these. So use that pattern, methods are there, find first match in that log. So this is our log, right? This is our log. And as usual, we if you remember, we use the either monadic collection. If it is a good record, we return a right object. If it is a bad record, we return a left object. That same thing can be used here. If it is a good record, convert it into an Apache log class object. Convert it into an Apache log class object. So you are converting, because you are receiving the data as a string. Each string will be converted to Apache log. That's what we are doing here. So you can hover on that. As of now, you can see that it was a D stream of string. D stream of string. And if you hover on access logs, after parsing here, you will get as a D stream of Apache access log. We converted into an D stream of Apache access log. So Apache access log is nothing but few fields are there, members are there. We have IP address, client ID, user ID, date, time, method, request URL, protocol, response code. All these steps are there. So we are doing our ETL process like error handling. We could have joined with some other data. Anything could be done. We haven't still used our broadcast because we are still using our IP address. So this IP address has to be converted to country code. This IP address has to be converted to country code. That we are doing here. Get all the viewed products, we have this where we are using that broadcast object. Slight other changes are also done. We may not require all the fields. We only required few of the fields. We require only few of the fields. Only those few of the fields are taken and IP address is converted. Some other stuffs are also we are doing there. So this is error handling and ETL process. Before that we did the offset management. Before this we did the offset management. Then we are doing our error handling and ETL process. Then actual our analytics is being done. Our actual analytics is being done. So when we convert, we have the product here because if you see here, we have a product. Product name is given here. Our class object contains that product name as a field name. So every time you get a product, we want to count how many times this product has been viewed. Hence we say every time we see a product, we say count as 1. Then we say reduce by key. For every unique product, you will get the total count with this. We have already seen this. Map each product to a key value pair where we will get this. Then there is an API called save to Cassandra. You just call the save to Cassandra, then we specify what is the Cassandra database name. Key space is nothing but database name. Page views is the table name. We will see this. Page views this is already been created. And you use some columns. This is the column name is page, which is nothing but the product name. Views will be. So if you see here, when we do a reduce by key, it returns a tuple. I mean, each record will be in the form of a tuple where the first element of the tuple will be the product name, second element of the tuple will be the count. You have to always have in the form of a tuple when you want to save the data into a Cassandra. And first element of the tuple will be mapped to the first column specified here. Second element of the tuple will be mapped to the second column specified in the Cassandra. So if you can initially you can always create a table. So the table is also here, log table.sql. You just run this script on your Cassandra console. So this is how you create. Instead of you say create database in MySQL, here you say create key space in Cassandra. If not exist, our key space name is log events key space. Then then you use that database. Then you create table. Create table if not exist. We have page views table. We want to know how many times a page has been viewed or the product. Log volume by minute. Status counter is nothing but how many times we are seeing 200 OK. How many times we are seeing 404. How many times we are seeing 500 error something. Again, we have created one more table, visits by country. Using that country IP address, we can get to know from which country we are getting more and more requests. So we are creating some 4 tables. You can also create a referrer table. You can also create a user agent table where you can get to know from which referrer we are getting more and more traffic. From which, using the user agent table, you can know whether we are getting the a request from the mobile or a desktop, whether from iPhone or all those stuff. Analytics can be done. So each table has two fields, two columns, country name and what is the count. Similarly, status also has the status code and the count. So the same logic is being applied to other analytics also. Save to Cassandra, take the response code and make the count as 1, then save to Cassandra. Similarly for country code also, save to. This is our actual analytics. This is our actual analytics. So if you can also go through the Avro streaming. Here there we don't need to do all this parsing. There we don't need to do all this parsing because it is already in the form of a class object. It is already in the form of a class object. We just use those things and do our analytics. Now since we have done the actual analytics here, we can, if offset is saved here, we get at least once semantics. So there will be duplicate data if the offset is saved here. So we have to we control when we ourselves do the offset management. We have a control on whether we want to achieve at most one semantics, whether we want to achieve at least one semantics, or whether we want to achieve exactly one semantic. But this is how the code works. This is how the code works. So we can run this program. So to run this program, again we need to have our Cassandra up and running. To run the Cassandra, we just say, so this will start a Cassandra cluster. So the Cassandra cluster is up and running. Cassandra cluster is up and running. You can open one more terminal and there is a Cassandra client like we have MySQL client. There is a Cassandra client we can connect. So we are connected to Cassandra client. There we say show databases in MySQL. Here we say describe key space. We say describe key spaces. So as you can see here, we don't have that table, that database. We can create that database. We had created a database with a different name. Drop key space, I will say logs. Instead of this, we will create, just copy paste this in your client. So table is created, the database, everything is created. So if you do a select star from page views, as of now, nothing is there. As of now, nothing is there. So you can run this streaming application. You can run this. Either you create a jar of this and do a Spark submit. We have already seen how to do a Spark submit. You can do that, or you can just right click and start running this code from here itself. Does it take some input parameters? Let me check. Because we are reading everything from the configuration file, I don't think so. Any input parameters are required. Just run this log analyzer. This is our Spark streaming application. It will start connect to the Kafka cluster and start reading the data from there. Finally, it will save the data to Cassandra. We can also see the logs initially where the offset is being created. Can we check whether the offset is created here? Okay. Yeah, you can see that this Kafka folder got created. I think some logging we have disabled. So if I do a get on, Kafka, as you can see here, offset 0, sorry, a partition 0, we have only one partition there because we have created only one partition. Committed offset is 2000. If I do again get here, again get Kafka, committed offset became 4000. As and as we are running, we are committing the offset. Again, if I do get, so it is keep on committing the offset. So as soon as we read, we restart our application and we start reading the from here, it will start reading the data from this offset onwards for this partition. For every partition, you will be saving the offset in this fashion. If you have 5 partitions, it will be 0, some offset, 1 colon offset, 2 colon offset, 3 colon offset, 4 colon offset. That's the way it will be happening. So again, if you go and check Cassandra, the data should be returned to Cassandra here. So as you can see here, a particular page has been viewed how many times? Because already we had started the producer long back, hence we are getting all these very fast. So we can also say select star from page visits by country. So you can see that from China there is 2466. From US there is these many views. From India there is 368 views. So this is how an end-to-end pipeline looks like. This is how a end-to-end pipeline looks like for our Spark streaming application. We are continuously sending the data to Kafka, or Spark streaming is reading the data from Kafka, processing it, and saving it. Now, even if I restart, when I restart this streaming application, it will start reading the data from that particular offset. So I think this record is coming because we are having our log 4K properties. So let's stop this application. Crashing a streaming application as good as we have abruptly stop this. So when we restart now, so the last, so the last offset that was read was 7,000 records, 7,390. So from here it will start reading. So if I run my application once again, Spark Streaming, right click and run this. So it should connect to the Zookeeper now. So you can see here reading offset 7390. So it will start reading the data from that offset. It will not start reading data from the starting. Wherever it had stopped, it will start reading the data from that offset. That's how you start reading. That's how you handle the errors in case of any application failure. This is how we use handle the error through manually handling the offset management. But this project, at max it can achieve at least once the semantics. Here we are not, I haven't written the code for exactly one semantics, but you can achieve that also. I mean, I think somewhere I had seen the code where it is available in the GitHub. You can take that code and integrate with that so that that will become a good exercise. Where exactly one semantics can, where the idea here is instead of storing the offset to Zookeeper, store the offset to Cassandra itself. Store the offset to Cassandra. So I don't know which one was that. Then this also is good. There is a Cloudera blog on offset management, and one more GitHub link was also there. I will share that. So offset management for Kafka with Apache Spark Streaming. There's a good blog. You can whatever I have discussed, the same thing is there, but it also says where all you can save the offsets. You can save the offset to HDFS, storing the offset to HBase. All the code is also available. Saving the offset to Zookeeper. Sorry, this is HBase because HBase also requires Zookeeper. Similarly, storing offset to Zookeeper. This is a Zookeeper offset. Saving the offset to Kafka itself. We can also approach that. So there is one here. This code, I think this code says how to store the offset to Cassandra itself. This is not the one. I will share the code. Probably you can integrate that. So that's the end-to-end pipeline how a Kafka streaming and Cassandra, Zookeeper, Spark, everything comes together and we can achieve a end-to-end pipeline. So I hope this project was clear. You can go through the video once again. You can go through the code, start executing that code. Once you execute, you will get a good hands-on on that. I would recommend doing that. Probably you can also try out the Avro one. You can also try out the Avro here. So let's wind up the session here and let's continue tomorrow. Tomorrow we'll be looking into the dataset APIs, how we can use the datasets in Spark. Thanks, thanks everybody. Good night and have a nice day. Good night and have a nice day. Thank you, thank you. Bye, bye.